In 3.2, the first part, we were looking at compartmental analysis, and we're still going to be looking at compartmental analysis in a sense, but now the things in our compartment are going to be populations. It could be populations of living things, it could be radioactive populations, but we're in some kind of system. So the first and kind of most basic type of population growth or decay that we deal with is when we suspect that the rate at which the population changes, so we could consider this the growth, or it could be a decay rate, is proportional to the population. So K is our constant of proportionality. P is the amount occurring. So if you think about bacteria, the more bacteria you have, the more you're going to get when it doubles. If we start with, let's make these bigger. If we start with 2 cells and then they undergo mitosis or meiosis and they split, then you've got 4. So when we doubled, we went from 2 to 4, that's an increase of 2. But if we have 4 and they divide, then we're going from 4 to 8. So that's from 4 to 8, that's an increase of 4, where from 2 to 4, that was only an increase of 2. So the rate at which the population is changing is proportional to how many you have in your population. If we have 1,000 and it doubles, it's still doubling, but it's going from 1,000 to 2,000, so we're increasing by a lot more. So the rate at which it's changing is related to how many we have. Now, this is somewhat an oversimplification of what most likely goes on as far as bacteria and a population, whether it's an animal population or whatever, because that doesn't consider disease, it doesn't consider predators, it doesn't consider death and things like that. So there are more complicated models, but this model is referred to as the Malthusian model. And for short time periods and for kind of closed systems that the time period is not incorporating very much loss, then this can be a fairly accurate model. So let's look at solving this. So in this differential equation, our variables are P and T. K is just an arbitrary constant. It's our proportionality constant. So we can separate and integrate. We can move the dt to the right, and we can move the p to the left. So if we divide both sides by p, we would have a p on bottom. If we multiply both sides by dt, we would get a dt on the right. So we could rearrange it to look like this. When we integrate both sides, k is a constant, so let's leave it outside of the integral. The left side integrates into natural log of p. The right side, when we're integrating a constant, we just pick up our variable and then plus. So to get rid of the natural log so that we can solve for p, we're going to do e to both sides. So e and natural log undo each other. Our population can't be negative, so there's no need to leave it in absolute values. If we have a sum in our exponent, then we can write this as a product. E to the c times e to the kt. Remember, if we're multiplying and our bases match, we add the exponents. So if we have added exponents, we can write it as a product with like bases. E to the c is a constant, so we can rewrite that as c. And then e to the kt. So population, that's a function of time. So if we're given some initial parameters, then we can find c and we can find k. Now, often in this situation, we might need to know 2 different data points. if we know the initial amount, let's say we have an initial of 1,000, then if we substitute a 0 in for t, we would get c e to the k times 0. K times 0 is 0, e to the 0 is 1. So we get c times 1 is c. And we're told that that population when time is 0 is 1,000. So that can give us c, but that doesn't give us k. So in order to find k, we need another data point. So we might be told that after, depending on our situation, our time could be in different units. We're told that after 2 years, that now our population is increased to 3,500. So that's another data point. That's when t is 2, population is 30. So that should allow us to find k. So we can replace the population with 3,500, put in place of t 2, and then we can solve that for k. Before we take natural log of both sides, we would want to divide to get rid of that coefficient. So e to the 2k is 3,500 over 1,000, or 3.5. Now we can take natural log of both sides. When we take natural log of both sides, the natural log and e cancel, and we can divide to get k by itself. So k is about, let's see, natural log of 3.5 divided by 2. Let's go to 3 decimals, 0.626. Notice we were growing. We went from a population of 1,000 to a population of 3,500, so that's a growth. Our k is positive. If we have a decay, we would end up with a negative k there. So our population function for this situation is 1,000 e to the 0.626t. And then we can use that model to predict the population at various times. This formula, this differential equation that will apply whether it's a population of people, of animals, even if it's a radioactive decay situation. If you have radioactive particles in a system, then the particles that are radioactive, they're going to seek to become stable. So after a while, if you have something that's radioactive, it's going to give off a proton, and then it's going to go to neutrality. Well, if you have lots of radioactive particles in your system, then whatever your decay rate is, then you're more likely to have a larger amount of atoms giving off protons and becoming neutral. But if we have a small population, if we have a small number of atoms that are radioactive, then in a set time, not as many are going to be changing. So large population, start the clock in a certain time period, we're going to have a fair amount going from positively charged to neutral. But if we have a small population, then we're not going to have as many changing. So we still have the same relationship. The rate at which the particles are changing is proportional to how many we have. When we have a lot, our change is significant. When we have just a few, our change is not as much. So in doing these problems, we want to go back to the basic equation that the change is proportional to how many we have. We want to solve that differential equation. We're going to come out with something like this, and then we use our data points to find C and K for our specific example. I do want to see you solve the differential equation. While this is a standard formula here, I would like to see how you get that formula, that you know where that comes from and how to attain it. Now, another situation that we're going to come across is when we're removing material from our system at a constant rate. So if it was just this portion, there's a problem from homework that says we have the rate at which the mass of fish is changing is proportional to how much fish we have in our pond. Instead of doing it by quantity of fish, they're doing it by the mass of fish. So the rate at which the mass is changing is proportional to how heavy the fish are in there. If you only have 2 fish in there, not a lot of mass, then they are going to grow, but that change of their mass is not going to be very significant. Where, let's say, 2 fish put on 2 pounds each per year, then you have an increase of 4 pounds. But if you have 1,000 fish in a pond and each fish puts on 2 pounds a year, then you're going to have an increase of 2,000 pounds. So a few fish, even though per fish it's the same growth, your overall growth is less when you only have 2 fish than your overall growth would be when you have 1,000 fish. So the rate at which the mass is changing is proportional to how much fish you have in that pond. In this case, we're letting mass, or M, stand for the mass of fish. But here, I'm using C. We could use another letter there. Let's use R for remove. Not sure what letter they're using in my math lab or in the book. But we might each year be removing a constant rate or a constant amount. So each year we might be taking 2,000 pounds of fish out of the pond. Then in that case, this would be 2,000 pounds. Or each year we might be taking 20,000 pounds of fish out of the pond. In that case, R would be 20,000. So R is not dependent on T. R is just a constant in this situation. Now, we could write an equation, or we could have a situation where at different years we're removing different amounts of fish. But here, we're planning on removing the same amount of fish each year, and we want to see what happens when that occurs. So the rate at which the mass changes is proportional to the growth. So this is going to be the growth part minus how much is taken out. So output, or I'm sorry, let's call that growth. We said the growth is proportional to how much we have in there, and then we're taking out the output. So let's see what and how we would solve that. So the only variable on the right side here is M for mass. So this one we can separate and integrate. M is a variable, the others are constants, so we can divide both sides by this. So those cancel, and we can multiply both sides by dt. So those cancel, so we get dm over k times m minus r, where k is the proportionality constant and r is the rate that we're taking fish out. And then we just have 1 dt on the right. I marked the wrong thing. I wasn't supposed to mark that out there, but we're left with km minus r on the bottom here, but on the right side the km minus r is canceled. So on the right side, that we're just integrating a constant, so we pick up our variable and then plus c. On the left side, this is just going to be a du over u. If the denominator is u and m is our variable, then the derivative of km minus r, k is a constant, the derivative of our variable to the first power is 1, r is a constant, so the derivative of that is 0. So we get this. So we need a k here, and when we integrate this, we need a k on bottom. If we multiply the inside by k so that this is du, and that's u, then we have to divide by k out front. And I guess I didn't write my integration there. So that leaves us 1 over k out front. If we integrate du over u, that's natural log absolute value of u. That's always going to be positive. We're not going to have a point where we have a negative amount of fish in the pond. So we get 1 over k natural log km minus r equals t plus c. We want to move the k to the other side, so multiply both sides by k. So natural log, and I'll be careful saying that. Km was the amount of growth, R was the amount that we're taking out. So it could be that that's negative if we're taking out more than is growing. That's not necessarily the how much we have in the pond. That's just the growth and removal in the pond. So it is possible that that's negative. So we do have to be careful with our absolute value there. Anyway, if we distribute the k, we have k times t. If we multiply a constant times a constant, that's just a constant. And then to get solve for m, we need to do e to both sides. So those cancel. So km minus r, e to the kt times e to the c. In place of e to the c, I'm just going to put a capital A there. Or I guess we can use a capital C. We don't have a C anywhere else. All right, so add r to both sides. So r plus c e to the kt. Divide both sides by k. So those cancel, so we get m equals 1 over k times r plus c e to the kt. So remember r, that's how many pounds or what mass of fish we're removing. K is our proportionality constant. C is just a constant of our integration. So R is something that's going to be most likely given. You're going to be told how much you're removing from the pond per year. C and K are things we would need to find. So since we have two different unknowns, then we would need two different data points in order to find those. Now, as I've looked back, just glanced at my math lab, they actually give the proportionality constant here. It could be found without it being given to us, but that would end up making things pretty complicated because just notice in a previous problem when we had an initial value, let's say we had an initial mass of 2,000 pounds of fish. Then when we substituted a 0 in for time, we would get a 1 for this, which would leave us C. R is something that we would be given, but we would still have a K out front. So we would have a C and a K still in that equation. So we would have two different unknowns there. And to find two different unknowns, you have to have two equations. So then when we would substitute in, let's say we were told that after a year, our mass was 2,800. So then if we put a 1 in for T, we would have a K in our equation, and we would still have C that we don't know. So we would have two equations, two unknowns, and we would have to solve and find C and K. And the problem they give, they're nice in that they tell us a proportionality constant. For example, they might tell us that the growth rate is 2 per year or 3 per year. So we substitute that in for K. Once we know what K is, then we can use an initial amount of whatever our initial amount is, maybe 3,000 pounds. If we know K, when we substitute 0 in for T, e to the 0 is 1. That leaves us C. We know R. If we know K, then C would be the only unknown in there, and we could solve that for C. And then, depending on what they want to know after that, now that we have our equation, we can solve for whatever we want to. If we want to find out when the mass is 0, we could take our equation once we know our constants. We could set it equal to 0, and we could solve to find when we would have a mass of 0. If we wanted to know when we have a different mass, then we could put that mass in and solve for when we would have that mass. If we want to know the population or the mass at a given year, we could plug in a number for T and get the mass in that year.